Yeah, so then you have to infer the night. All right, let's go ahead and get started. Any questions before we begin? So I think at some point I'll have to do a lab makeup session. I haven't quite determined when. I'm kind of thinking maybe midterm week, that Friday, because we're starting to have people miss stuff. I know I have at least 3 people that missed the popcorn lab. I don't know if people are missing today, but I'm trying not to have people miss labs, and I don't want us to do online makeup labs because that's just not a good experience. But so that's kind of my thought is, so tentatively put that on your calendar of like Friday, midterms week, would probably have a makeup lab session for probably the 4 or 5 labs that you could have potentially missed. And then thinking about doing another one probably around that finals week, but again, we'd have to look at the calendar. So just keep that on your radar. And then if you're absent for like recitation and you missed a quiz, then we'll have to arrange that with the testing center. And then of course, Same thing with missing the midterm. If you know you're going to miss the midterm, a few people have already let me know, we could do that ahead of time. And then if you were sick that day, you'd have to go through the testing center. All right, so let's continue on unless there are questions. Let's finish up isotope representation, and then we need to hit up chapter 3. So this is just another way to represent isotopes. So yesterday we were looking at neon 20, kind of written in this form, but you'll find you can also see it written this way. So you could see like C13 as well, or 13C, or carbon 13, carbon 14. And so like we were kind of looking at, so we're kind of seeing this with our carbon example, if you remember from Tuesday. So we were kind of hinting to where we're going with this relative abundance. And so what we find is that each of these isotopes occur in different relative abundances. And so isotopes are one of those cool things where we're not really sure why the phenomenon of isotopes occurs. And then what you'll also notice is that certain isotope combinations are unstable, so like carbon-14, for example. And it starts to happen when your nucleus, or your number of neutrons, starts really outweighing your number of protons. That seems to cause like weird instability. Obviously, as you go into the heavier elements, they can kind of handle a large number of neutrons better. But with carbon, right, it's so small. So carbon-12, right, that's stable, while carbon-14 is now radioactive. But all these things relate to their natural abundance. And so basically, you can, right, characterize your sample of neon or whatever element you're interested in, and then determine the natural abundance. And so, for example, neon 20 is your most abundant of almost 91%. Neon 21 is only 0.27%, and neon 22 is almost 10%. And so let's practice some symbol writing. So what would be the atomic number, the mass number, and symbol of a chlorine isotope with 18 neutrons? So how would we write that? And if you're in the chat, you can always put your answer in the chat. Oh, I don't have any ones handy. You have to hang on to your yellow copy. I could flip. I'll flip to one, and let me know if you need me to flip back. I'll flip back for a second. All right, so what do we get for our symbol? So what letter symbol should I write? So Cl, and then what's my mass number up top?
35.
So 35, right? So the mass number, that's the biggest number that should go on top. And then, so you looked up chlorine's element 17, and then so it sounds like you added 17 plus 18. give you 35. And then, so what number goes here?
17.
So 17 goes here. So remember, 17 is also equal to Z, which is again our atomic number. And then no charge was indicated, so we can leave that as a neutral there. Any questions about this? So now let's move on to ions. So again, isotopes, right? Different number of neutrons. So those are how those differ. Now ions, this is where we have charged atoms, and so we're going to be either gaining or losing electrons. And so we'll typically see that cations form, and that's going to be a positive charge when metals lose electrons. And again, we've kind of gotten a taste for that with our oxidation states. So for example, right, we know those alkali metals like to lose one electron, and so that means that we can find them in the +1 state, and so we'd want to indicate that. And then negative ions, so we'll see that those are your anions, and those all tend to be those nonmetal elements, so fluorine, and then, oxygen, sulfur. Could also be nitrogen, 3-, etc. So then we can write that. So let's just say, let's look at magnesium 2+. So how many protons, neutrons, and electrons do we have? So how many protons does magnesium have? So I hear 12. So 12. How many neutrons?
12.
So 12. So there we could just make our best assumption. So you look at the periodic table, they didn't tell us which isotope, which is round to the nearest whole number for our purposes, unless you're given more information. And then how many electrons? So 10, exactly. And so there's two ways to think about that. You could either start at the neutral, so you know the neutral would have 12 electrons since we have 12 protons. If we have a +2 charge, you can think about subtracting those 2 electrons. Or you can always set up the algebra, so +2 is equal to our protons plus our negative amount of electrons, or minus electrons, whatever works best for your brain. And then so solving, so then you get number of electrons is 10 there. Let's try another one. So what would everything be? And so let's try this example. So strontium 101 2+, so protons, neutrons, electrons. So how many protons does strontium have? So here 38. For some nods. And then how many neutrons in this one?
63.
63. Is that what everyone got? And then electrons?
36.
36. Excellent. And so let's do one more example. So let's do an isotope, this time of selenium. So we'll do selenium 79 with a 2- charge on it. So again, protons, neutrons, electrons. So take a minute and we'll go over it. All right, let's do it. Protons for selenium.
34.
34. Neutrons.
45.
45. And electrons.
36.
Excellent. And so with that one, you saw it was a -2 charge. So again, you could start at the neutral, but you see a negative, so you have to add those negative electrons to bring you to 36. Or you could set up the math, either way. All right, good job on that. So finishing up the chapter, so we were going over, so this atomic mass then, so kind of going back to isotopes, the atomic mass is called our atomic weight or standard atomic weight. And so again, that atomic mass, that's the one directly beneath the element symbol on the periodic table. And this atomic mass represents, again, the average mass of the isotopes. And so again, this makes sense. So we look at our periodic table, and especially if we look at chlorine, for instance. So there's no chlorine atom that weighs 35.5 grams. I don't even think there's a chlorine isotope that weighs 36 grams, or at least if there were, it's very low abundance. So I don't think it exists, but this is just, again, the average. And so we would calculate the atomic mass with the following equation. And so all this is saying, it makes it sound really complicated, but it's just a summation of your percent of your whatever isotope 1 is times that mass is. And so all this would be for chlorine. So we look at chlorine. So naturally occurring chlorine, it only has 2 isotopes. So its first isotope is chlorine 35, which has an exact atomic mass of 34. Oh, sorry. How do you silence your doorbell? Anyways, sorry. So it has an exact mass of 34.97 AMU. And its second isotope is 24.23% with an exact mass of 36.97 AMU. So for this, we'd have to set this up. And don't forget your sig figs. I know it's really painful, especially when we start doing some of these percent abundances, but keep track of those. So, and then we have to convert this percent to a decimal, so 0.7577, so that's our fraction, right? Times our mass, so our mass 134.97 AMU, plus, and again, luckily chlorine only has 2 isotopes, so this isn't too terribly painful. So converting this to a decimal, 0.2423 times our mass. And so now we just have to punch that in. And hopefully I didn't punch anything in wrong. So I think I punched it in right because I got what the periodic table says. So hopefully you got the same. So 35.45. So now we see where that mass comes from. And so sig figs, I might have already messed this up on the sig figs. So multiply this. I'm going to have to go back. So that gives me 4 sig figs, so 26.4 or 26.50 plus, sorry, just trying to figure out my sig figs. And so in your homework, or I think it's one of the labs, you have some calculating abundances. And so you'd want to do it kind of step by step. And so there I have 4 sig figs, but I can only report to 2 after the decimal point. So I'm going to round it to 35.45 there. So I was limited by that first value. And so the next question is, well, how do scientists either observe this, and how can we see the different masses? How do we know that they're different masses? How do we know the abundance? And so we have a really awesome technique called mass spectrometry. And all it does is measure the mass of atoms and molecules. And so we look. And so these are all tend to be some sort of time of flight mass spectrometers, but you have your little sample here. And so if you've ever seen a mass spec, they're pretty small, or they can be. And depending on the setup, they're either auto samplers, or you might have to inject your sample. But basically, you inject your sample through a very small needle, and then it gets vaporized, and then they ionize it. So then your molecule starts to fall apart, and so you can only see the ions. And so these ions get accelerated, and then they get detected. And so you have different types of detection modes. So you can look at positive ions, and then you would see all the positive ions. Then you can flip it, see all the negative ions. So you can only detect one at a time, at least for the most part. But then this magnetic field separates the ions based on a ratio of mass to charge. And so ideally, they all just have one charge and to their mass. And so basically what you would get, so if you shot some chlorine through your mass spec, or something that contains chlorine, so this would contain one chlorine atom. And so if it contains one chlorine atom in your sample, then you would get peaks that correspond to your 2 chlorines. So you would have one at 35, and that would correspond to the relative abundance. So this would be about 75% abundance versus 24%. And so you can see that right reflected in their ratio of about 3 to 1 just with the height. So that tells you their abundance, and that tells you, again, your isotopes. And so when you're trying to identify your compound or trying to see, did I make what I think I made, and you have a chlorine in there, then you're going to be looking for this isotopic pattern. And so you might not have a mass at exactly chlorine, like if you're observing some sort of fragment that had chlorine on there. So it would have, right, the mass of 35 plus this, plus the mass of 37 plus this. But you would still have 2 distinct peaks that would be 2 mass difference apart. And then if you had other isotopes, so why I specify this is only 1 chlorine, so then you could start having combinations of different isotopic patterns. And so if you have 2 chlorines, for example, you have several possibilities, right? So one of those chlorines could be isotope 35 and isotope 35, or they could be 35 and 37, 37 and 35, or 37 and 37. And so this is the same mass-wise, but then you would kind of get now 3 isotopic peaks, and of course we'd have to sum those up to get what the relative mass differences would be. So you would have 70, 72, and probably 74. But you would have a three-peak pattern kind of like this, and they would again be separated by 2 mass difference there. And so now here's a mass spectrum example for bromine. And so bromine, it looks like there are actually 2 bromines in this sample. And so you can tell that, I think this actually might just be bromine itself. So this makes sense. So this is Br2 shot through a mass spec. So we can see that it's fallen apart. And so they made 2 ions of Br minus. And bromine has, again, this very distinct isotopic pattern. So bromine has 2 isotopes in about 50% abundance each. So one bromine 79, the other bromine 81. And of course, note, right, its average mass is about 80, so that makes sense. And so with bromine, you see this nice isotopic pattern that indicates you have 2 bromines in there. So again, you have that 79, 79 mass there, and then your 2 different combinations of 79 and 81 to give you that larger peak in the middle, and then this peak is from your 81 isotopes. And so this is really powerful, again, for chemists. You can easily see, do I have bromine in there? Yes, no. And then you can move on with your life. So here's just another example of what you would see. So this is bromopropane, so just basically a 3-carbon chain with a bromine on it. And so again, you can tell right away, oh, yep, bromine's on there, since you have that distinct isotopic pattern. And then notice the mass difference to your next mass peak has a difference of 79, again, giving you a big hint that that's bromine. Skip over the practice for now. All right, any questions on chapter 2? So now we'll shift to chapter 3, which is chemical changes. And so chemical changes are anything that alter the composition, so highlight that. And again, we're just talking about a rearrangement of atoms. So during a chemical change, atoms rearrange, transforming the original substances into different substances. And I'm sure many of you are familiar with rusting, so that's something that we see every day and probably a chemical change that we don't want to occur, but it happens. So we have iron atoms, so they would be in our metal, in our pattern here, and of course oxygen comes along and is hanging out, and so then it eventually reacts, starts forming our iron 3 oxide, which is rust, and of course you end up with your rusty nail. And so when we write our balanced equations, we want to be able to write our reactants go on the left side, products are on the right. And so this is also just like your recipe book. So it's just telling you what's going in there. So how many cups of flour do I need? How many eggs do I need? It's the same sort of thing. What ratio are our ingredients in? And so in this case, we have 1 equivalent of methane reacting with 2 equivalents of oxygen. And so this is a combustion reaction. Then we also want to indicate the states, so we know, again, how this reaction is going to proceed, because your reaction will change, depending on the state as well. And so this is a gas phase reaction, so indicated by the little g's, and then we are going to produce a gas as our product, and then also H2O as a liquid. And so again, these chemical equations just provide information. They give us our formulas, and again, our ratios, so our states. So we indicate G for gas, L for liquid, S for solid, and then AQ means an aqueous solution, so that's generally going to be some ionic compound dissolved in water, or maybe like HCl in water. So this could be anything as long as it's in H2O. That's all that it means. And so it gives us our relative numbers of reactant and product molecules. So this is also leading to stoichiometry, right? Our fancy word for just our recipe book and how we scale it up and down. And so this can be, of course, used to determine weights of reactants used and the products that can be made. And so again, I was saying, especially if you want to continue and do chemical research, or if you want to do drug design and pharma or anything, if you're going to be synthesizing stuff and making molecules, you're going to be doing this every single day of your life. Is what am I making? How much stuff am I putting together? All that good stuff. And so we can balance it by two different ways. And so again, the amount of every substance used and made in a chemical reaction stays the same. And so we have our law of conservation of mass. So we could either do mass balancing, which I don't generally encourage, just because I think it confuses people. But if you understand it and you want to just go for it, go for it. But I think it's best if we look at it by balancing equations, by balancing our atoms and sticking with kind of our ratio formula. And so that is all, again, called stoichiometry. And so if we look at this, so they wrote their balanced reaction out. And so we can balance out our atoms. And so let's just see. And so I would just do bookkeeping on the bottom as your scratch work. And so you can just tally up. So we have carbon, hydrogen, and oxygen. And again, they already balanced it for us. But then you want to just check. So how many carbons? So 1 on the left side, 1 on the product side. Hydrogens, 1, 2, 3, 4. 4 there. And then on our product side, 1, 2, 3, 4. And then oxygens, 1, 2, 3, 4. Oxygen, 1, 2, 3, 4. And so how to balance these is you usually want to start with the elements that are kind of involved in the most things first. So you'd want to balance your carbons first, and then save your oxygen for last. And know that this is just kind of a guess and check game. So you're going to try, one thing, play around. If it doesn't work, start over, take a new guess. But don't be afraid to get the wrong answer, is what I'm saying. So let's try this first one. So take a couple of minutes or so. See if you can give me the coefficients, and we'll go over it. And still watching the chat as well. So how did you approach this? What did you maybe try to balance first?
I balanced the oxygen first.
So that's what I would do. So what did you try to do to balance the oxygen?
Since it was an odd number for the first one, I just did 2.
So if we put a 2 here, then we have to put a 3 here. And then, so now we can start kind of tallying. So we have cobalt, oxygen, and carbon. So cobalt, oxygen, carbon. So let's see, oxygen, looks like there's 6 on the left right now and 6 on the right. Okay, but now cobalt, so I have 4 right now. So let me go ahead and put a 4 there. See how that works. And then so carbon, so right now I just have 1. And then on the product side though I have 3. So let me put a 3 coefficient there. And I believe that's balanced now. And I see a lot of nods in the audience, so that tells me y'all got this as well. And so again, we just balance by putting a coefficient in front, right? So this is our either molecule or ionic compound that we're adding. So something that's ideally we can buy from a bottle, right? We're going to add that to our reaction. And so we just want to know what ratio do we need to add everything in. And so it looks like we need 2 equivalents of this cobalt 3 oxide to 3 equivalents of carbon to give us 4 equivalents of cobalt and 3 equivalents of CO2. And so how do chemicals react? How can we predict how they react? And so the periodic table, we were touching on this, is that it's arranged in order of increasing mass, but then it's also arranged in, we said, columns, since there are certain sets of properties that recur periodically. And so Mendeleev is considered the father of our modern periodic table. And so he organized it in the format that we kind of know today. And so what was key is he noticed that there were elements with similar properties, and so we placed them in the same vertical columns. He also saw that this happened every so often in a pattern, so probably every 8. So beryllium to magnesium is 8, magnesium to calcium is 8. And so he kept noticing these patterns repeating. And what was even cooler, at least I think this was cool, is he was able to even predict elements that did not exist or were not known yet at the time. And so he left little gaps. For instance, he predicted the germanium, so he called it ecosilicon, but it was below silicon, so like silicon, so it was really germanium. And so those rows of the periodic table are referred to as periods. So each time you go to a new period, that's a new quantum level or a new principal quantum level for electrons. So your first row just contains the first quantum level. So this has the S, so this is just the 1s. Then we go down to the 2s. So the first quantum level only has the s orbital. The 2 has an s and a p. 3 is spd. And 4 would be spdf. And of course, you could go on theoretically, but we'll stop there. And then our columns in the periodic table are either referred to as groups, or I usually use the word families. And so again, they all have similar properties. So we're starting to see that. So we've talked about these alkaline metals, that they're extremely water reactive. We are starting to go into the alkaline earth, how these are less reactive than the alkaline metals, but these are all still relatively reactive. So usually reactive with acids. We know about the halogens, that they're really reactive. We went over group 6, all our smelly groups and how they react. So again, they all share reactivity patterns. And so our periodic table does not explain why these patterns occur, just that we observe them. And of course, quantum theory explains why, so our deeper chemical understanding of our MOs and molecular orbitals, that tells us why they react. And so with our periodic table, you can see that they're roughly categorized by metals, nonmetals, and metalloids. And I like this one, it's a little bit more broken up. So you can see metals would be anything to the left of this metalloid. So you have your metalloid staircase, so it's labeled semi-metal on this one. Again, this is your metalloids here. Just highlight that. And then obviously this periodic table breaks it down into different classifications of metals. But then we all know that our nonmetals are to the right of our metalloids. And of course, these are gases. And then we can also specify a few other things. So sometimes people may refer to main group elements, or there's specific like main group research. And so anyone that is a main group chemist, they would typically be looking at kind of these elements are main groups, so boron, aluminum, silicon, gallium and germanium, nitrogen, phosphorus, arsenic. So these are generally your main group. And then of course transition metals. Those are just all here. And then these can either be called intertransition metals. Usually just hear the term F block metals or lanthanides or actinides. All right, so now let's look at kind of electron configuration and what they all have to do with one another. And so again, if we look at our alkaline metals, they all kind of follow this pattern. And let's go over, let's do electron configuration. I feel like this is going to take forever, this chapter. Oh, here we go. All right, so let's go over how to fill up the electron configuration. And this starts getting us into our orbitals as well. So if we start again over here, so we said this was the 1s orbital. So this is our lowest in energy. So we would fill that up first. So this is 1s1. And let me pull up another resource. So if you want to follow along, you can go to ptable.com. And so we were using this in the properties mode, I think last time, to look at the pretty pictures. But if you go over to the top on the electron mode, now it will give us the electron configuration and also oxidation states, or at least, again, the most common ones. So we start at hydrogen. So I click on hydrogen. It tells us the electron configuration right here, so 1s1. So again, it's element 1. If it's the neutral, it's just 1 electron. And then it shows us what that orbital looks like. So we have a nice sphere, so it's just a sphere that is for our s orbital. So then we go over to helium. So helium then fills up the s, so now this is 1s2. And then we can consider helium a noble gas since it's satisfied, so its orbital is complete. And so sometimes you hear the term that it's satisfied by the duet rule. And again, this only applies to helium since it only has a 1s orbital. It's filled up, it's satisfied, so now it's not reactive. So now we continue along, so going in order. So now this starts the 2s over here. So now this is lithium. And so if we go ahead and look at our alkali metals, we'll notice a pattern right away. And so this will be 2p, blah, blah, blah. We'll go back to that. So this is 3s, 4s, 5s, 6s, 7s. So these are all the S, and so they all follow this same pattern of NS1. And so that means, right, that they have one valence electron. They just have it in a different outer shell. And of course, what do you notice? As you go down, these shells are increasing, so we're physically adding more shells. That means not only is our radius getting larger, but what can we say about the reactivity? So it's increasing. And the reason why it's increasing is because, again, that radius is getting physically larger. The nucleus has a weaker hold then on that electron out there. And so cesium, right, is just ready to fly off at a moment's notice. So that's why cesium is super reactive. And lithium, again, you can handle it in air. It will oxidize, but not so explosively. And so they, again, all have that pattern, NS1. So if we go back to this electron configuration, now we can understand, again, why they always have that 1+ charge. And that's just showing that those alkali metals have that tendency to lose that one valence electron. And then, of course, that would give them a noble gas configuration. They're satisfied, and they can go on to bond and things. So now alkaline earth metals. So we've stated that they have a 2+ charge. I'm trying to write stuff on different periodic tables, probably not helpful. So now they all follow NS2. So they have a filled S shell. But then if you notice, so beryllium, you know, or once you get over here, so like boron, even though it has an S shell filled, it will still lose electrons and want to lose all these electrons. So this is not stable. So beryllium would be 2s2. And for the full electron configuration, you need to write 1s1, 2s2. And so we look at beryllium on our P table. So it tells us, and it gives us the electron configuration in two forms, so you can see the kind of shorthand, which for beryllium doesn't save us too much time. And so the shorthand is just indicated by writing the previous noble gas in parentheses like this, or in brackets, I mean, and then continuing on. So for beryllium, you start at helium and then fill up 2s2. And so you can see that written out explicitly, 1s2, 2s2. Beryllium, 1s1, 2s2. And so again, that repeats all the way down. That's why those have a 2+ charge on them. And so let's continue filling it in. And so if you're just going along the periodic table, so let's highlight a few things on this one. So this is our S block, so we were focusing on that first. So this is all S orbital base. So now, as we trek on, so we'll go from beryllium to boron now. And so boron starts our P block, so all this is our P block. And so this starts 2p, so boron's electron configuration would be 1s2, 2s2, and now 2p1. And so they just follow along, so carbon is 2p2, nitrogen 2p3, oxygen 2p4, 2p5, etc. And then so we can label down here, so this is 3p, 4p with gallium, 5p with indium, 6p with thallium, and of course 7p with these synthetics. I wanted to look at your textbook actually. Oh my gosh. I just want to log back into your textbook. All right. I'll try to look at it later. I was trying to reference what's information's in what chapter. And so you can click along and see the electron configuration. I want to see. I remember why I don't like your book. I feel like your book is like random trivia sometimes, and they don't present things in a way that I would, but that's fine. Yeah, I think I'm trying to give you chapter 5 now, because it's hard not to, but. I don't know why they put electron configuration without talking about all the quantum levels and everything. Well, anyways, I was trying not to overwhelm you with too much information, but you can kind of see, and again, this is apparently a preview for our next chapters. So these P blocks, they all have these kind of dumbbell shaped, and so you can see they're in different orientations. So there's 3P blocks, or excuse me, 3P subshells, so PX, PY, PZ. Each of those holds 2 electrons, and it's 6 across. So that's where that comes in. And so let's go back to filling this in so you at least know how to do electron configuration. And so it's relatively straightforward. So let's do chlorine's electron configuration for practice. And we'll do this together. And so let's start. So what do we fill up first? So S, so we need to start with our 1S. So 1S2, then what's next? So 2S, and then we fill it up, so 2. And then 2P, you have to fill it all the way. So how many fit in there? So count them, 1, 2, 3, 4, 5, 6. So 2P6. And then back to here. So this brings us back to, so 3S2. And then 3P, so what's chlorine? So 3P5, excellent. Right. And then I'm just going to do argon. And so it's 1 over. So instead of 3P5, what will it be? So 3P6, good.
Can you show us the abbreviation, like if we went off of neon?
So if we wanted to go off of neon, and so that's exactly what you would do. So that's the first previous noble gas, so back at neon, so for argon. Now we start at neon, so we'll just write that abbreviated, and then go from neon back down to our 3s. So now 3s2, 3p6. And so now let's look at where things start to get a little tricky with the electron configuration. And so again, if you need multiple copies of the periodic table, just let me know, because things start getting messy fast, especially as we lay all the fundamentals down. But, all right, so we were at argon, so we're here. Now we start, so things are normal right now, so we start at the 4s, so we can do our abbreviated argon, then 4s1, 4s2 for potassium and calcium respectively. And now here's where we start the Ds, but what did I say about what quantum level the Ds started at? So it started on the third one, but we haven't had any Ds yet. So this is 3D starting there. So whatever you need to do, label that. So then you're going to fill up all the 3Ds first. And then once you get back over here, now you're back to 4P. So make sure you write that down. So then you go 4P and 5S. So now you're back at 5S1, 5S2. Yttrium is 4D. And then fill it in as we would expect. Back to 5P. And then let's just go over all the oddities. So from xenon, you're at xenon. Now we go to 6s1 for cesium, 6s2 for barium, and then this is where I purposely use this periodic table because it is wrong in the sense that lanthanum should really be up here for 57. So lanthanum starts the 5D. Then we go from 5D, so lanthanum, so notice this is 57. Then cerium starts 4F, so this is 4F1. And then why I know that this periodic table is wrong is because the F can only hold 14 electrons. And if you count this, and you can always double check your periodic table, this is 15 across, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So, oops. So that's why I say put the lanthanum here, and that means that actinum should go here as well. Then this gives you your appropriate 14 across for your F block. And so you can kind of mark this off as our F block. And so where were we? So we were 4F, so we finished this out. So this is 414F with lutetium over here. Then hafnium starts back up with 5D2, but don't forget the 4F14 in the middle. And so let's do hafnium together so you can see what I'm saying. And so what noble gas can we start with for hafnium? Xenon. So we'll look at xenon. So we start with xenon, and so that brings us to 6s2. Then we have to fill up this 4f14 because it's stuck here in the middle. 4f14. And then that brings us back to 5d1, 2. And then always double check yourself. So I'll try to point out some oddities, but you'll notice that, again, with chemistry, there's always a bunch of exceptions. They can always do something funky. But what I care most about is it at least in the reasonable order that we would expect, and then do your total number of electrons add up? And so what I mean by that is, let's start with xenon. So xenon was element 54. So we'll start with 54. So 54 plus, and then each of these superscripts indicates an electron. So plus 2, plus 14, plus 2. So that gives us 72. And then does that match with hafnium? Yes, it's 72, so we have at least the correct total number of electrons. So I'll give you a preview into the discrepancies, and then we'll probably touch on them later when we actually talk about orbitals into depth. And so, for example, chromium is an oddity. So if you look at chromium, we would expect it to fill up with argon and then 4s2, 3d4. But again, we'll touch on why later, but it's more favorable for it to throw that other electron into the d orbital. And it's essentially because all those energy levels are really close. And so what it's doing, so chromium, what we expect, so you have your 4s, and then your 3d, so your 5d orbitals. So we would expect to go like this, but you always pay a price for pairing electrons, and so it must actually be more energetically favorable to just kind of throw itself in a geometry that would make them more degenerate, and then have an electron in each one instead. And so again, just take this in for now. We're going to go back to this over why this is and all these orbital pictures later. But I think my most complaints about your book are with the beginning chapters. But again, just hang with me, ask questions, and it will all make sense. So yeah, your book wants you to know electron configuration without you appreciating the orbitals that it is derived from, but again, that's a rant for another day. And so your book even has these exceptions listed here. And again, I'm not expecting you to know them. Just take them in right now, understand that there are exceptions, and you can always look at the P table to orient yourself. So for example, there are some other oddities. If you look at the F block series, so cerium is what we would expect. So we started with lanthanum, so 5d1. I said cerium would bring us to 4f1, so that's expected. But then if you move over to the next element, praseodymium, then it skips the D and goes straight to the F. And so again, I don't expect you to know that, just know that there are exceptions. And so probably on an exam, when we get to like more of the MO theory, I would ask questions as we would expect it to fill up like this, but it actually does that, and then you would explain why. All right, so hopefully we're all not confused on electron configuration. And so now it's just trying to give you what I say, like fun facts. And so your book is emphasizing your metalloids. So again, they're part of that zigzag line. And why they're cool is they can exhibit both metallic or non-metallic behaviors. And then these metalloids are also funky, is that they can lose electrons from the p orbitals and s orbitals to form cations, or gain electrons in their p orbitals. So those metalloids are super cool, and that's why on your periodic table they also have like funky oxidation states on there. So they're all, like especially nitrogen, I think it's like -3, +3, +5, and so all that is due to this funky thing. So they can gain electrons, add electrons, lose them. And so again, our nonmetals tend to gain electrons. So we've kind of emphasized that, especially with our fluorine. So again, if you haven't written these charges there, so you should have a -1 charge over this halogen group, because we know those tend to gain 1 electron. And again, that goes back to its electron configuration. They all have an NP5, so they're 1 away from that NP6 full, complete, happy electron configuration, so they tend to gain 1 electron. So same with oxygen, they all follow MP4 pattern, so -2 oxidation state. And then nitrogen, -3, again MP3, but that's where, again, it can gain or lose electrons potentially. And so we looked at those halogens, so again, emphasizing that NP5 electron configuration, hence why they're so reactive. And there's a typo in this note. And so that's just emphasizing your elements with predictable charges, although it left out zinc over here of 2+, and I believe silver's over here with 1+. All right, so let's go back to balancing equations. That's really what your chapter is about. And so let's just do some practice. Let's do these first 4 here. So I'll give everybody probably until like 11, at least 11:10. So we'll see if we can do that. So talk with your neighbor if you need. Come up with an answer, and we'll go over it together. So let's try to go over these. And if you're in the chat, you can post your answers, A, B, C, D, with the coefficients that you picked. And so just to note a couple of things, so I just want to point out, for example, chlorine, right? When you go to write it, so if this was a word problem and it said iron and chlorine were added together to make iron chloride, or iron 3 chloride, right? We write chlorine Cl2 because it's one of those diatomics. So don't forget that, all those things. So be remembering which elements are diatomics. And so that's why we have Cl2 here. So how do we balance this? You can give me the coefficients. What did you get?
2 iron plus 3 chlorine makes 2 iron.
Excellent. So is this what everybody got? Thumbs up. And then so just practice your naming as we do this. So again, this is iron 3 chloride. So iron, one of those variable oxidation states metal. We have chlorine, so -3 for there, 3 of them. So iron has to be in the 3+ oxidation state. All right, next one. Does someone want to give me the coefficients?
4 iron, 3 oxygen is 2.
Is that what everybody got? And so yeah, let's name this. So Fe2O3, what would that be? Remember your swap trick, you can back it out.
Would it be iron 3 dioxide?
So it would just be iron 3. And then we don't use our prefixes with ionic compounds. And then there's 3 oxygens anyways. But we just want to do iron 3 oxide. And so how I knew it was iron 3 is I just reversed the swap trick and saw, okay, well, -2 matches the oxidation state for oxygen, so nothing weird happened. And so that must mean that iron's oxidation state is +3. All right, so this one could have been a little tricky. My one hint for this is you have this SO4 group, and you could try to balance that as just one big group since it doesn't look like it splits apart. So do we get coefficients for this one?
2, 3, 0, 6.
2, 3.
Nothing.
Oh, so 2, 3. So we'd say 1, 6. Is that what everybody got? I see some nods. And so this looks good. And so let's just name what we have. So can we name this one? Iron 3 bromide, excellent. Plus, and then I'll give you this one. So we haven't covered naming polyatomics yet. Hopefully I wasn't supposed to cover that. But this polyatomic is called sulfate. And this is actually special because it's an acid. So this H2SO4. Does anybody happen to know what this is by any chance?
Sulfuric acid.
Yeah, nice. Sulfuric acid. And then let's see if you can at least, so what would be the oxidation state of this iron? So just back out your swap trick and that will help you. Iron 3, exactly. And so you wouldn't know this because again we haven't covered this, but this polyatomic SO4 sulfate has a -2 charge, so that's where that 2 came from. And so that makes sense then that this is iron 3, so that would be iron 3 and sulfate. And then last one, HBr, anyone happen to know it's an acid, so it has a special name. And so if you know HCl, HBr is the bromine equivalent. Yeah. I don't know if you know that or just went for the guess, but that was exactly it. So hydrobromic acid. So we could do more practice. I'm just trying to think if I want to do this one or not. So we haven't quite. We're like kind of here, but not. All right, do we have any questions over anything so far?
Could you give us a different example of, so with the iron 3 bromide, iron 2 sulfate, could you give us another example of how to use the swap trick to determine if it's an ion?
Like what the charge is?
Yeah, or just, I'm having a hard time conceptualizing the swap trick.
So if you have FeS, what would be the charge on iron? I'll do some more. All right, so let's look at these. And so for this one, if we wanted to use the swap trick, maybe I pick ones where you can't use them. Well, we could, so we have our -2 here. And then they're balanced kind of 1 to 1. So I guess, because you could back it out. So if they're balanced in a 1 to 1 ratio, but then you back it up, well, you know sulfur doesn't have a -1 charge, right? So that means that you can just multiply everything times 2, and then that kind of works where you have, okay, this should be -2, and if I know this is -2, and this has to match, that has to be 2 plus. I don't know if that helped with your question or not. But then, so that would be iron 2 sulfide. And then, so what about this one? So what would the oxidation state for cobalt be for this one?
So nitrogen is -3, right? Which means it has the acid 3, but it's cobalt 2.
Well, these are two separate problems, sorry. So then this would be cobalt 3 nitride. And then I threw this one in there. So how would you write the formula for cobalt 2 nitride then? And so maybe the swap trip is more relevant for this. So if you do cobalt, so this is 2 plus, and then you said nitrogen was 3 minus. So then you could swap them, so CO3 and 2, and that at least gives you the formula. If I had thought of this example better, I would have done CO3 and 2, and then you could have backed out the swap trick to get you back to the cobalt 2. Let me try to think of a good one. So let's try. Sorry, I'm trying to make something that makes sense.
Thank you for the impromptu examples.
I think that works. Yeah. So what is the proper name of this? So what would the name of this one be? So tungsten and 2, exactly. So arsenic, you could back it out. Does it match with -3? Yes, it does. And so this 2 plus also matches, and then you can just do your math. So 2 times 3 is +6. -3 times 2, -6. So that all works. Yeah.
What do you do if when you back it out, they don't match?
So if they don't match, then just something's off by a factor. That usually happens with, like, let's try 10 here. So if you back out this tin sulfide compound, so we don't know what oxidation state tin is in. So back it out, this gives us 2, this gives us a 1. But then what's wrong with that? So we know sulfur is really -2, but if we times everything by 2, that gives us tin of 4, sulfur -2. Okay, that seems to match better. Then double check your math. So 4 times 1 is 4 plus, -2 times 2, -4. So now we know we have tin, 4, sulfide. Yeah.
Just like a side question to this. Every time they bond hydrogen with halogen, it's always made a strong acid. Maybe it's like the hydrochloric acid and hydrochloric acid.
Well, so it depends what you mean by strong acid. So a strong acid, by the technical definition, is one that completely disassociates. And so that the answer would be no, because not all of them completely disassociate. So HF doesn't completely disassociate. But if you mean strong as a sense of will hurt you, then yes. Like HF will mess you up, so you definitely don't want to get HF on you.
You get like a hydroiodinic acid.
Yeah. So hydroiodic acid is a thing, hydrobromic, hydrochloric. Yeah. Any other questions before we end lecture officially? And so the plan is we'll end lecture officially. I'll give you all, 10 minutes to stretch your legs, take a break. And then we have our quiz. So then we'll do our quiz. So it's open note, open everything, except open partners. So it's just individual. And then my plan is once you're done with the quiz, because I don't want to keep track of time. I know some people have like accommodations in here, and I didn't really time this that well anyways. So just, take the rest of class to finish it, and then you can work on whatever you need to work on. Ask me questions. We can always, step out into a hall too if we need to give people more time to finish the quiz. So whatever. So that's my plan for the rest of class. So at least stick around for the quiz before you go abandoning class for whatever other things you need to get done. So we'll reconvene back here. I have 11:24, so I'll give you 10 minutes. I'll give people an extra 5 minutes before we start the quiz. And then thank you all. If you join on stream, we had some classmates on stream. And if ever y'all need to join on stream because of illness, just let me know and I can send you the live link. Or maybe y'all have figured it out. All right, thanks again, chat, for your participation.